Let's take a look at another example problem here from ME12 Dynamics for our Module 10. So in this example here, we're given this initial diagram where we can see we have this T-bar right here hanging from the ceiling at a pivot point at point O. We can see the center of mass here is given to us at point Y bar from this pivot point up here at O. So there's our G for our center of mass there. Down here at the intersection, we have our point A, and the tips of both ends, we have our B over here. And see over there, we can see that B is 1 foot off the center, C is 1 foot off the center, and our total length from point O down to this member BC is going to be 2 feet. So now in our problem statement, they tell us that there's 2 rods assembled as we see there, each rod weighing 10 pounds. Now they want us to find the location of the center of mass G, so this is what we're calling here our Y bar right there, and we want to also calculate the moment of inertia about an axis passing through that center of mass G of the rod assembly. So for our plan of attack for solving this problem, what we're going to first do is look to solve for our central moment of inertia for each rod individually. So we're going to deal with each rod independent of one another. And then we're going to use our parallel axis theorem in order to determine our I sub G. So again, I decided to type this one up here rather than doing it out by hand so you guys can follow along. It's going to get, again, a little bit messy as we're looking at a diagram like this here. And we clearly want to make sure that we can find all the internal things that we're looking for, especially our Y bar there. So really, other than what the initial given diagram, all they really give us is the mass of each rod is 10 pounds. So again, finding our center of mass, the location of our center of mass, our Y bar, and our moment of inertia about an axis passing through that center of mass for the rod assembly are what they ask us to solve for within this problem. So plan of attack, again, find that central moment of inertia of each rod individually, and then use our parallel axis theorem as our governing equation here in order to solve for our I sub G. So not too much difference between our problem statement and our setup page here. So again, the main thing here is that we know that this mass and then all of our dimensions in this given diagram. So before we get our solution, what we want to do now is figure out what our key equations are. So that's what we're going to do here on this page here. We recall that our plan was to find our moment of inertia for each rod and then the system as a whole to find that Y distance to where that is located from our O point. And we also need to use our parallel axis theorem to determine our I sub G. So first thing we want to do is take a look at this relationship here that we see. So this is our formula for determining our center of mass. So our X sub G, Y sub G, and Z sub G, depending on where we're at. And our mass moment of inertia about a rod, we recall here, is I sub G is equal to 1/12 ml squared. And this comes from over here. We can look this up in our appendice of our book or one of our other textbooks as a reference to get this relationship for a rod. So as we begin our solution, what I've decided to do here is draw out a simplified 2D version of our given diagram so we can see this over here on the right. You can see within this I have my rod from O to A and I have my rod from B to C here. What I'm looking for is this G value here, some distance Y bar away from our O here for the entire system. So what I want to do before I look for that is to break this down in terms of its individual parts here. So I'm going to look at rod OA and rod BC separately. So for rod OA here, I can find the center of mass of my rod OA right here. It's right in the center of this. Its total length of OA is 2, so our center of mass is located halfway down this for a rod at 1 foot down. Now I'll do the same thing over here for my rod BC. So my rod BC over here, we have boom, boom, our center of mass is located right in the center of that. Same thing, distance from A to C is 1 foot there, but our distance from this rod all the way down, from our point O all the way down here to our rod, where the center of mass is going to be that distance of 2 feet. So now when I plug into my formula for determining the mass center here, my Y bar is equal to the summation of MI, YI all over the total mass here. Well, the first part of this is the mass of OA. So my mass of OA is the weight of OA, 10 pounds, was given to me in the problem statement, divided by my acceleration due to gravity of 32.2 feet per second squared. So this whole term there gives me the mass of rod A times that distance right here, my Y distance right here. So my Y distance here for rod OA is right here, my 1 foot, Plus now I go over next to my separate mass of rod BC. So here's my rod B to C there. Again, same mass, 10 pounds, divided by my acceleration due to gravity of 32.2 feet per second squared, times, again, y distance here. So my y distance from my origin point O up here is 2 feet. So I plug that in, 2 feet times the mass of that. My total mass is just adding those two together, the sum of those two masses up above there. So weight divided by gravity, sum those two together. And when I do out my mass here, I can then get my y bar, which is then equal to 1.5 feet. So that's the first thing they asked us to solve in the problem for, was this y bar here. And we did that by taking this relationship here for the formula for determining the mass center. So now what we can do is we can recall our parallel axis theorem here and calculate our I for OA. So again, I'm going to do this separately for each individual component of our system here. So again, first I'm going to look at my rod OA. So my rod OA right here, I know my I sub g from my key equation that I looked up is 1/12 ml squared. So that goes right into here for my parallel axis theorem. So my total I here is equal to my I sub g plus my md squared. So I plug in this relationship there into this equation here for my I sub g for this rod IOA. So right here, IOA about O is equal to 1/12 ml squared from this relationship here for my I sub g plus my md squared here. So now I can go down and start plugging in my known values to this relationship here. So that's what I do. Okay, my 1/12 here, my mass, my m right here is my weight divided by my acceleration due to gravity again. My length here is the total length of this guy here, which is 2 feet right there. So this is 2 feet squared plus my m, same mass right there, times d, the distance there, which is 1 foot squared. So when I plug all this in, I get a relationship here that IOA about O is equal to 0.414 slug feet times second squared. So now this is just solving for this, for our inertia here for rod OA. Now we need to do it next for rod BC. So now what we can do is we can do that same calculation for BC. So again, use the same formula here. So we have our I, BC, our maximum inertia here of our rod BC is equal to, there's that same relationship right there, our 1/12 ml squared for a rod. So we can plug in for that there, plus md squared. So the main difference here is this d value here, now that we're dealing with rod BC, is going to be 2 feet instead of 1 feet from its distance here from O up here at the top. So plug in, we end up with 1/12. Our mass is our weight divided by the acceleration due to gravity, plus here my L squared, the length of the rod is 2 feet, plus our mass again, weight divided by gravity, times our d value, again, that 2 feet from this over here, squared. We do out our math here, and IBC is equal to 1.346 slug feet squared. Now we want the total mass moment of inertia here, so we add it for that of each rod. So our I sub O is the sum of both of those, our IOA and our IBC here, so we can plug in those numeric values. And we find that this is 0.414 slug times feet squared, plus 1.346 slug feet squared is equal to, when we add these together for the summing them, is 1.76 slug times feet squared. Now we need to take this value for our I sub O, plug back into our parallel axis theorem. So again, use our parallel axis theorem here, and we can back out our I sub g now out of this here, because that's what it asks us to solve for here. So we know our I sub O. We can plug in for our md squared for our whole system here, and our d now is this y bar that we solved for at the very beginning. So we plug in this here. We know our IO by summing those together from the previous slide here is 1.76 slug times feet squared. This is equal to our IG, which we're solving for, plus our mass, which is weight divided by acceleration due to gravity. And this is weight of the entire system, so it's 20 pounds because each rod weighs 10 pounds. Times now our Y bar here for our D and our parallel axis theorem that we'd already solved for at the beginning of the problem. That's 1.5 feet squared in this relationship here. So our only unknown is our I sub G. We can back out our I sub G here, and our I sub G is equal to 0.362 slug times feet squared. And that's our final answer for this problem.